Hello everyone. In this video, we are going to discuss about the topic effect of dielectric on capacitance of class 12 physics from the chapter electrostatic potential and capacitance. See, we have already discussed about the parallel plate capacitor and we derived the expression for the capacitance of a parallel plate capacitor in our previous video. If you want, you can watch that. I will provide the link in the description box. So let us move on to our this topic, effect of dielectric on capacitance. See, we know that a capacitor have two conducting plates. One is a positively charged plate and another one is a negatively charged plate. And you see, here the surface charge density is plus sigma, and here on this plate the surface charge density is minus sigma. And you see these two capacitor plates, they are separated with a small distance, small letter d, and there is an electric field in between the two plates of the capacitor, which is vector E, directed from the positive plate to the negative plate of the capacitor. And let us see how the capacitance of a parallel plate capacitor is modified when a dielectric is present in between the two plates of the capacitor. See, dielectric, they are actually bad conductors of electricity, but they can hold electrostatic charges. So, suppose there is vacuum. Initially, there is no dielectric kept in between the two plates of the capacitor. Suppose there is vacuum in between the two plates of the capacitor. So, that time we have the expression for the electric field in between the two plates of the capacitor as sigma is equal to E is equal to sigma by epsilon 0, where epsilon 0 is the permittivity in vacuum or free space. So E is the electric field present in between the two plates of the capacitor. Sigma is the surface charge density. Okay, that is charge per unit area. So since I am taking the two cases here, that is I am comparing the two cases where the dielectric is present in between the two plates of the capacitor and where there is no dielectric present in between the two plates of the capacitor. So I am taking when there is initial condition, when there is vacuum in between the two plates of the capacitor, I am representing this electric field as E0. Okay, so E0 is equal to sigma by epsilon 0. Now we have the potential difference between the two plates of the capacitor. I am taking it as V0, that is equal to what? Electric field times the distance between the two plates of the capacitor. Okay, see, when we have discussed about parallel plate capacitor, we have just represented the electric field with the E, potential difference with the V, capacitance with the C. Here we have to compare the two situations. So that is why I am taking these as E0, V0, etc. Okay, now we have the expression for the capacitance of a parallel plate capacitor. Here I am representing it as C0. This C0 is equal to what? Epsilon 0A divided by D. Okay, or this can also be written as what? C is equal to Q by V. So Q, charge on the capacitor, divided by the potential difference V0. Now consider there is a dielectric, this yellow colored one, there is a dielectric inserted between the two plates of the capacitor, fully occupying the intervening region. See, this dielectric get polarized due to the electric field which is directed from the positive plate of the capacitor to the negative plate of the capacitor. Dielectric is polarized means there will be a slight separation between the charges present in them. Okay, and you see this effect is actually equivalent to two charged sheets with surface charge densities minus sigma p and plus sigma p. Okay, that is here we have a dielectric present in between the two plates of the capacitor. Because of this external electric field, they get polarized. That means the charges present in them, there will be a slight separation of charges present in a dielectric. Okay, so this will be equivalent to this. That is, we will be getting another two sheets, charged sheets with surface charge density minus sigma p and plus sigma p. Okay, so what will be the net surface charge density on this plate? This plate, it will be plus sigma minus sigma p, that is sigma minus sigma p plus sigma minus sigma p. What will be the net surface charge density on this plate of the capacitor? Already minus sigma is there, then plus sigma is here. So if I take minus sign outside, I can write it as minus of sigma minus sigma p. So here we have plus sigma minus sigma p. On this plate of the capacitor, we have minus sigma p. That is, the net surface charge density on the plate is plus or minus sigma p. Okay, that is if you neglect the sign plus and minus, if you take only the magnitude of that surface charge density. So after the dielectric is inserted, the surface charge density becomes sigma minus. So you see, before the dielectric was inserted, that is when it was vacuum between the two plates of the capacitor, the electric field present in between the two plates was E0 is equal to sigma by epsilon 0. Now you see, now we have a dielectric present in between the two plates of the capacitor. So now the electric field in the dielectric becomes what? That is, the effective electric field will be E is equal to, now the surface charge density is sigma minus sigma p divided by epsilon 0. Okay, electric field is surface charge density divided by epsilon 0. When there was vacuum in between the two plates of the capacitor, surface charge density was sigma, so sigma by epsilon 0. After the dielectric is inserted, the surface charge density becomes sigma minus sigma p. So now the electric field is sigma minus sigma p divided by epsilon 0. Okay, now what will be the expression for the potential difference between the two plates of the capacitor? Now I am taking it as V. So you see, V0 is equal to electric field times the distance between the two plates of the capacitor. Okay, so you see, now it becomes V is equal to the electric field E. E is the electric field after the dielectric is inserted. So E times the distance between the plates of the capacitor. See, whether there is a dielectric present between the plates of the capacitor or not present between the plates of the capacitor, there is no change in the distance between the plates. Okay, so E into D. So E is what? Sigma minus sigma p divided by epsilon 0 into D. So the potential difference between the two plates of the capacitor becomes like this. Now you see, for linear dielectrics, linear dielectrics are materials in which the induced polarization is proportional to the electric field. That is, in linear dielectrics, the strength of polarization will be proportional to the external electric field. And for linear dielectrics, the sigma minus sigma p, this will be proportional to sigma. Okay, sigma minus sigma p, that is the surface charge density after the dielectric is inserted between the plates of the capacitor. Sigma was the surface charge density before it was inserted. So for linear dielectrics, the sigma minus sigma p will be proportional to sigma. Okay, now when we replace this proportionality sign with an equal sign, we have to write one proportionality constant here. I am writing it as 1 by k. So 1 by k into sigma. That is, sigma minus sigma p, this is equal to sigma by k, where this k is a constant which is a characteristic of the dielectric, and this constant is known as dielectric constant. So k is a constant which is a characteristic of the dielectric, which is known as dielectric constant. So you see, we have the potential difference as sigma minus sigma p by epsilon 0 into D. Now in terms of k, how does it change? You see, V is equal to sigma minus sigma p into D divided by epsilon 0. The sigma minus sigma p can be replaced with sigma by k. Then epsilon 0 is there in the denominator, D is there in the numerator. Okay, now what is the sigma? Sigma is actually surface charge density, which is charge per unit area. Okay, then K is there, epsilon 0 is there, D is there. That is, the potential difference between the two plates of the capacitor after the dielectric is inserted between the two plates can be written as V is equal to Q into D divided by epsilon 0 A into K. So you see, we got the expression for the potential difference between the two plates of the capacitor as V is equal to Q into D divided by epsilon 0 into AK. Now, let's see be the capacitance with dielectric between the plates. Okay, we got C0, which was the capacitance of the parallel plate capacitor when there was no dielectric present in between the plates, which was actually given by this expression Q by V0. Okay, or that can also be written as what? Epsilon 0 A divided by D. Now, when there is a dielectric present in between the two plates of the capacitor, it will be having a new capacitance. I am taking it as C. So, C is the capacitance with dielectric present between the plates. Okay, so this C can be written as what? Q by the potential difference V. What is this potential difference V? The potential difference V is Q into D divided by epsilon 0 AK. So, Q into D divided by epsilon 0 AK. Okay, so multiplication with reciprocal. So when we do that multiplication with reciprocal, this becomes what? Q into epsilon 0 AK divided by Q into D. Okay, so you see this Q cancelled. So you will get the new capacitance C as epsilon 0 A by D into K. So you see epsilon 0 A by D was the capacitance of the parallel plate capacitor when there was vacuum in between the two plates of the capacitor, or when there were no dielectric present in between them. But when there is a dielectric of dielectric constant K present in between the two plates of the capacitor, then its capacitance changes. The new capacitance is epsilon 0 A by D into K, where epsilon 0, that is a permittivity of free space. Okay, see this epsilon 0 into K, no? Epsilon 0 into K, this is actually the permittivity, okay, permittivity of the medium. Epsilon 0, that is a permittivity of free space. Epsilon 0 into K, that is a permittivity of the medium. This epsilon 0 into K, this is taken as epsilon, which is the permittivity of medium. Now you see, from this equation epsilon 0 K is equal to epsilon, we can write K is equal to epsilon by epsilon 0. Okay, see, or E by E0. Okay, so you see this K, it is the ratio of epsilon divided by epsilon 0. Epsilon is the permittivity of the medium. Epsilon 0, that is the permittivity of free space or vacuum. So you see epsilon by epsilon 0, which is the dielectric constant K. So this is a dimensionless ratio, that is actually called as, this dimensionless ratio is actually called as the dielectric constant of the substance. Okay, now you see we have C0, which is the capacitance of the parallel plate capacitor when there is no dielectric present between them, as epsilon 0 A divided by D. Now when there is a dielectric present in between the two plates of the capacitor, capacitance is epsilon 0 A by D into K. So this can be written as what? C is equal to epsilon 0 A by D is actually what? C0. So C0 into K. Okay, or we can write K is equal to C by C0. Okay, see this K, which is the dimensionless constant, which is called as dielectric constant. This dielectric constant K, it is a factor which is greater than 1. Okay, so you see dielectric constant K, it is the factor by which the capacitance increases from its vacuum value to when the dielectric is inserted between the two plates of the capacitor. Okay, see this K is greater than 1. K is greater than 1 means C by C0 is greater than 1. That is C is greater than C0. That is a new capacitance is greater than the initial or the earlier capacitance. That is by inserting a dielectric, the capacitance increases, that is more charge can be stored. That is, you see, when there is a dielectric present in between the two plates of the capacitor, the strength of the electric field actually reduces or decreases. Okay, we know that electric field is actually the potential difference times the distance between the two plates of the capacitor. So you see, when there is a dielectric present in between the two plates of the capacitor, the electric field strength is reduced. Okay, see D is a constant, which is this is a general equation. Okay, so D is the distance between the two plates of the capacitor, so D is a constant. So when electric field strength is decreasing, then V also must be decreasing. Okay, that is V also must have reduced. That is, potential difference reduces. If the total charge on the capacitor plate is kept constant, that is Q. If Q is kept constant, then the potential difference is reduced across the capacitor plates. That is, you see we have C is equal to Q by V. When there is a dielectric present in between the two plates of the capacitor, electric field strength reduces. So potential difference also reduces. When potential difference decreases, that is when V decreases, C increases. That is capacitance increases. So in this way, the dielectric increases the capacitance of the capacitor. So in this video, we have discussed about the effect of dielectric on capacitance. I hope it is clear to you. Thank you.